When lacking information or being curious about other, it is the time to Google it. In today's digitalized world, around 1.9 billion websites exist, indicating that the internet is a vast resource of knowledge. But it's still hard to get the expected benefit or taking the advantage without facing side effects, as that huge number of web pages may be paired with knowledge dispersion. Knowledge dispersion is where the choices are too many to choose from, or where useless pages waste readers' time without giving them the expected result. Thanks to search engines, with only one click on the search bar, we can get thousands of pages answering our query. Is the point here? Of course no. The great advantage that search engines like Google offer to us is the precise ranking of results according to their importance. How is it done? Thanks to the PageRank algorithm developed by Larry Page and Sergey Brin, software engineers at Google. After a long history of multiple trials and different implementations of different methodologies, internet web pages are now ranked according to their popularity. What is the meaning of that? Simply, the most important page is the most popular one, and so on.
Hello everyone, so now let's get to the technical part. Now users from all over the world navigate across a connected network of web pages. At any time, every single user has the choice to randomly pick another link to visit. One of the questions on which we're going to be focusing on today is how one define a ranking depending on the web network model. In this video we will be explaining the Markov chains, which is considered one of the web network models. Eventually we will be building the PageRank algorithm using these Markov chains. This algorithm is literally the backbone of Google search. Now we will be dealing with powerful mathematical ideas involving these Markov chains models. A Markov chain is defined by a few specific properties. In the context of a web network, individual web pages corresponding to states of the Markov chain and going from one state to another one involves a transition probability. In this chain, any user can go from state 3 to state 1, with transition probability equals half. If a user is at state 2, they have 100 chance of transition to state 3. In the context of a web network, it's common for transition probabilities to be assumed based on the number of outgoing links. So for instance, if a web page has 3 outgoing links, we assume the user is equally likely to transition to each of these states with probability 1/3. We can also change these probabilities based on some prior knowledge or data. So if altered the distribution as follows, it would assume that users are much more likely to click on an outgoing link to web page 2. Now, the problem we consider today is ranking the importance of states in the Markov chain. A simplified real model here is to imagine a user got 4 web pages from a search query. These web pages will often reference each other, so they form a Markov chain. How should we rank the web pages to show an end user? The first question here is how we should define the importance of a state in a Markov chain. If we have a variety of users surfing web pages, what might be a good way to rank the relative importance of each web page? While one natural way to think about the importance of web pages is to imagine a single user continuously going from one page to another page according to the Markov chain model. At each point in time, the user is going to be at a particular state of the Markov chain, and we could maintain a counter for the number of times they visit the state over a long period of time. The states that end up being visited more often can naturally be thought of as having a higher rank. Actually, counts we consider to be long-term behavior as a distribution on the proportion of time a single user spends in each state in this special Markov chain. If we ran this experiment for a long interval of time, the distribution stabilizes, and this distribution is generally called a stationary distribution of a Markov chain. Here, the stationary distribution indicates that the most important state is state 2, where the explanation of the possibility is that a random user who serves this network for a long interval of time will spend about 26% of their time at state 2. What we're gonna dive into in this clip is how exactly might we find a stationary distribution of a Markov chain. In what circumstances do these stationary distributions even exist? How we can efficiently compute them and calculate them. To be able to calculate the stationary distributions, we must first digest and understand so carefully the concept of how we can make model for Markov chains mathematically at its core. So, for about 10 weeks of continuous work, passing through multiple challenging stages, we have done our best to produce the research in a perfect way. We have put into consideration the clear language with wide range of lexical and grammatical resources beside the totally unique words and phrases representing the topic, as we have rephrased every single text to match the research style. Now, you will be seeing our final report, and that's all. Thanks for watching. I hope you enjoyed it. Assalamu alaikum wa rahmatullahi wa barakatuh.